Hey, this is Presh Talwalkar. Here are 7 puzzles for geniuses. See how many you can solve. Puzzle 1. We have a square garden plot that measures 4 units on each side. From the bottom left corner, take 1 unit from the left side and take 1 unit from the bottom side and cut out a 1 by 1 square. We've planted 10 trees in this garden. The challenge is to divide the plot into 5 equal shapes, where each shape has 2 trees each. So how can we solve this problem? Let's work through the problem logically. Let's create lines that are vertical and equally spaced across this plot, and let's do the same thing where we have horizontal lines that are equally spaced. How many squares have we divided the plot into? This will be a total of 15 squares that are 1 by 1. We want to divide the plot into 5 equal shapes. So if we want to divide the area, we need 15 divided by 5, which equals 3 squares per shape. So let's consider composite shapes that are made of 3 of these unit squares. One possible shape is to have 3 squares in a row. So let's try to divide up the plot with this kind of shape. We would fit 1 of these in this corner, then we squeeze another here, we have a 3rd shape up here, and we have a 4th shape, and finally we're left with an L shape. We cannot use 3 squares in a row, so we cannot have 5 equal shapes. If we were to try it in another way, we're still going to get stuck when we get down to this final shape. We have an L-shaped square, so it's not going to work. So we won't be able to get a shape that has 3 of these squares in a row to work. So let's just consider the shape that is remaining, which is an L shape made up of 3 of these squares. We'll start out by filling this irregular plot right here, and we'll see if we can fill up the rest of the plot. We'll do 1 in the corner, we'll do another in the corner, and we can just fill up all 4 corners, and voila! We have divided the plot into 5 equal shapes, and all we need to do is check that there are 2 trees in each of these shapes. And this is in fact true, so we have found a solution. And that's the answer. Puzzle 2. You are given 6 identical matchsticks. The challenge is to arrange the matchsticks in such a way that every single matchstick is touching all of the other matchsticks. So let's start by experimenting. Let's imagine we just take a group of 3 matches. Well, it'll be easy to arrange them into a triangle, and each matchstick will be touching the other 2. Let's arrange the other 3 matchsticks into a triangle, and each of these will be touching the other 2. So if we could somehow join these shapes together, we would have a solution. But if we overlap these triangles, we get very close to the answer, but we are missing it by 1 spot. This match, for example, is not touching the match that will be parallel to it in the other triangle. So you can see that we will not have every single matchstick touching all of the other matchsticks. So this is a close approximation, but it's not a total answer to the puzzle. So we're going to have to adjust our shape just a little bit. So let's go ahead and change this shape. Let's start out from the beginning. Instead of arranging them into a triangle, let's consider a slightly different shape. So now we have 3 matches, and each of these is touching all of the other matches. For example, these 2 matches are touching, and these 2 matches are touching, and finally these 2 matches are touching. So we do have a triangle shape between these 3 matches, however, it's formed in a slightly different way. So let's arrange the other 3 matchsticks in this same shape. Now, in each of these shapes, each matchstick is touching the other 2 matchsticks. So all we need is that each matchstick in the shape is touching all the matchsticks in the other shape. So let's overlay the 2 shapes on top of each other. We have the left shape, and now let's put the 3 matches right on top of it. And this is a solution. Each of the matchsticks is touching all of the others. What an incredible arrangement. Puzzle 3. We have 4 coins arranged in a diamond shape. You have to rearrange the coins in such a way that they are 4 coins in a row. Now they might not be in a row in this exact horizontal shape. It might be in some rotation of this horizontal shape. But in any case, you want all 4 coins to be in a row. But there is a rule. Each move you can make, you can only slide a coin to a new spot that's touching the other 2 coins. So let me give you some examples of legal and illegal moves. Let's say you take this coin at the bottom and you slide it and you touch these other 2 coins. That would be a legal move. But now let's say you take this coin and you just move it over here. This coin is only touching one other coin, so this would be an illegal move. So let's go back to the beginning. We have 4 coins in a diamond and we need to arrange them so that they're 4 in a row. So how do we do it? I have to admit this was quite a challenging puzzle for me, and even after I saw the solution, I had to think about it twice in order to present it. So here is one way to solve it. Start out with this coin on the right and move it around so that it creates 3 in a row so that it's a straight line up and to the right. Now, take this coin and we will do an incredible move. We will create a gap and it will touch the bottom 2 coins. From here, we'll take this coin on the bottom right and we will just rearrange it to the other side so that we have 2 coins and we have a gap. And finally, we take this coin and we fill the gap. And finally, we will have 4 coins that are all in a row. Incredible! Puzzle 4. We have a geometry problem. We have a shape that is made up of many squares. On the right side of the figure, we have a square that measures 18 centimeters, and we need to figure out the length of the square that's shaded in blue on the left. So this is just a straight up geometry problem. Let's work through it step by step. Let's take this 18 centimeters and let's translate it to the top. We now have 3 squares that measure 18 centimeters, so each square is going to measure 6 centimeters. We now have 3 squares that measure a total of 6 centimeters, so each of these is going to measure 2 centimeters. 2 of these squares will make up a larger square, so each of these squares will be 4 centimeters, and there are 3 of these. So this entire square will be 4 plus 4 plus 4, which is 12. We now have 4 smaller squares, so each of these will measure 12 over 4, which is equal to 3. So this entire larger side will measure 12 plus 3, and this will be equal to 15. And that is the side of this square, which is 15. And finally, this blue square will be 1/3 of that, so each of these sides will be 5. Therefore, this blue square measures 5 centimeters. And that's the answer. Puzzle 5. We have another geometry problem. We have a composite shape made up of rectangles and squares, and the problem is how many squares are in this figure. Let's solve the problem methodically by counting the number of squares of each type. So we'll start by counting squares of the smallest size. So this will be easy. We have 1, 2, 3, 4, 5, and 6 of these squares. Now, let's consider a square that's made up of 2 by 2 of these. So a larger square, how many of these are there? You have to be a little bit careful. So here's one in the upper left. We have another in the upper right. We then have a third right here in the middle. Then we have one in the left corner, and then we finally have one in the right corner. So this will be a total of 5 squares. Now let's go up in size by one more square. So we're counting 3 by 3. This is the one that most people miss. Most people won't consider 3 by 3, but there is a 3 by 3 square in this diagram, and there's just one of them. So we're going to add that. And finally, we go up one more, and that will be the entire shape, and that will be one more. So the total number of squares will be equal to 6 plus 5 plus 1 plus 1, which equals 13 squares. Puzzle 6. The first box says 7688. The next box will be 2688. Then we have 768. The fourth box is 336. And finally, we have two boxes without any numbers. The challenge is to figure out what the missing numbers are. So we essentially have a sequence of numbers. A good way to approach this problem is to consider the difference between consecutive numbers. So if we consider the first two numbers, they have a difference of 5,000. Then we have a difference of 1920 and a difference of 432. There's no obvious pattern in looking at the differences of consecutive numbers. So let's consider another way. Let's consider the ratio of numbers. So going from the first to the second, we would multiply by 961 over 336. Then we would multiply by 7 over 2. And then we would multiply by 16 over 7. So okay, we don't have an obvious pattern again. So let's approach the problem in a different way. Let's look at the number 336. What is its prime factorization? It is equal to 2 times 2 times 2 times 2 times 3 times 7. Now let's just look at some of these numbers. If we have 2 times 3, that will be equal to 6. Then if we have 2 times 2 times 2, that will be equal to 8. So 336 is equal to 8 times 6 times 7. But wait a minute, look at the number that's just before it. It has the same digits. So we could say 336 is equal to 7 times 6 times 8. So 336 is exactly equal to the product of the digits in 768. Let's see if this pattern continues. Let's take a look at 2,688. If we take 2 times 6 times 8 times 8, we exactly get 768. If we try this one more time, we have 7688, and the product of these digits will exactly be equal to 2,688. So we now go to 336, and we take the product of these digits, and this will exactly be equal to 54, and that will be the next number. We then take 5 times 4, and we will get that's equal to 20, and that will be the final number. So the two missing numbers are 54 and 20. Wow! Puzzle 7. We have 10 squares arranged in the following shape. We're going to place 4 different knights. We have 2 white knights and we have 2 black knights. The challenge is to swap the positions of the black and the white knights. In the end, you should end up that the 2 black knights are in the spots where the 2 white knights are, and vice versa, the 2 white knights are in the positions where the black knights are. But there are rules to this game. So the knights themselves move like in a regular chess game. So if you have a knight, it's going to move 2 up and 1 over, or it will move 2 over and 1 up. This will be an L shape. So if we have a knight in this grid, these are the different possible places that the knight could move to. So each knight is moving just like it would in a regular game of chess. And just like a regular game of chess, each square can only have 1 piece. So you can't move 2 knights to occupy the same square. This would not be allowed. But there is one difference to a regular game of chess. Unlike chess, you do not have to alternate moves between white and black. So let's say you take the black knight and you move it up here. In a regular game of chess, you would have to alternate to a white knight. But in this puzzle, you are allowed to move that same piece again, or another black knight. So you could move this black knight to another position, and that would be a perfectly legal move. So the puzzle is, how do you swap the positions of the white and black knights? There is absolutely no trick to this puzzle. Anyone who's determined could solve this problem. But I will warn, it's not an easy puzzle to solve just by guess and check. It's a very tedious problem if you approach it just on this chessboard and try to visualize it. But fortunately, there's a wonderful mathematical trick to solve this problem. This puzzle appeared in the 1990s horror video game, The 11th Hour. And I heard about it from the Fields Medal interview from the renowned mathematician, Jun He. Here's an excerpt from the interview. They asked him, what kind of mathematics did you like best in school and at the university? Do you have a favorite math problem from back then? He replies, I may be atypical among professional mathematicians in that I was neither very good nor intensely interested in mathematics in school and at the university. I do, however, have a few early experiences that may now be characterized as mathematical. For example, I was playing The 11th Hour in middle school, a 90s video game in a horror setting, and there was the following chess puzzle. So what happened when he tried to solve it? After hundreds of ad hoc attempts, spending all my energy for more than a week on this puzzle, I almost gave up. Then I realized the L-shaped move of the knights and the physical appearance of the irregular chessboard are irrelevant. Only the relations between the squares matter. Thus, the problem was equivalent to the problem of exchanging the positions of black and white knights in the following graphs, where the knights now move from a vertex to one of its neighbors. I was completely blown away by this ingenious approach to solve the puzzle. So let's work through it step by step. Let's first remove the knights from the squares, and let's number this top square as 1. Where can a knight go from this square? There's only one spot that the knight can go, and we'll label this as square 2. From here, the knight could go back to square 1, or if it proceeds to a new square, it can only go to one square, which we will label square 3. There's only one new square a knight could go from here, and we will label that as square 4. From here, let's say the knight goes to the bottom row, and we'll call this square 5. The knight can't proceed to any new squares from here, it could only go back to square 4. From square 4, there is one other spot we could go to, and this we will call square number 6. A new square that you could go to from here, we will call as square 7. Then we could proceed to a new square, which we will label as 8. We can finally go down here, which we will call square 9. And then we complete the tour of all of these squares and call this as square 10. From square 10, you can only go back to square 9. So now let's connect squares where a knight could legally travel between. So knight could go from 1 to 2, 2 to 3, then to 4. From 4, if the knight goes to 5, the knight will hit a dead end and then has to go back to 4. But the knight could then go to 6, and then 7, 8, 9, and finally it'll be a dead end at 10. So instead of analyzing the problem in terms of squares and knights, let's look at this as a graph. We have 10 different nodes, and we have edges that are connecting nodes where a knight could legally travel between. We don't need the graph to be in this shape. We can actually unwrap the graph so that we have it in an easier to understand shape. So let's go ahead and unwrap this graph. Let's move the node 1, then we will put 2 next to it, and then 3 next to it, and then 4 next to it. From here, we have one branch that goes off to 5. We have another branch that goes off to 6, and then 7, and then 8, and 9, and 10. So now let's place knights on this new graph. In the original puzzle, the knights were placed with a white knight on square 1, a white knight on square 2, a black knight on square 3, and a black knight on square 5. So on the new graph, let's place white knights on nodes 1 and 2, and black knights on nodes 3 and 5. So the question of swapping the knights' positions in the original puzzle can be tackled by swapping the knights' positions on this new graph. Looking at this new graph, it should be quite clear how to swap the positions of the knights. The key to the whole puzzle will be the node number 5. This will be a place that you can park a knight and all of the other knights can pass by it in this L shape. So let's go ahead and use this strategy. Let's first take the 2 white knights and the black knight on 1, 2, and 3 and move them out of the way. So let's go 3 to 4, then the black knight will go 4 to 6, then it'll move to 7 and to 8. This will clear some room for the 2 white knights. Then we'll move the white knights to the spots of 7 and 6. So we'll move this white knight out of the way, and we'll do the same thing for the other white knight. This will clear the path for the black knight parked at 5. So it can proceed without any hindrance all the way to node number 1. Now we need to move this black knight into node number 2. So we need these white knights out of the way. So we'll get the white knights out of the way, and we need to park the black knight into node number 5. So we've cleared the way, and now this black knight can go into node number 5. It'll be out of the way, so now the white knights can proceed down, and then we will clear a path for the black knight. So we move this white knight to node number 6, and we have a clear path for the black knight to go to node number 2. We'll just proceed and go ahead and do that, and now the white knights can come back up. So this white knight will be positioned at node 3, and this white knight will get parked at node number 5. And voila! In 40 moves, we have swapped the positions of the knights. This would have been tremendously complicated to do in the original puzzle, but it was a cinch with this translation of the problem into a new graph. What a genius and amazing puzzle! Thanks for making us one of the best communities on YouTube. See you next episode of Mind Your Decisions, where we solve the world's problems, one video at a time.